Good evening, everyone. Thank you for joining us for Astronomy on Tap, the Los Angeles edition. I'm Dr. Cameron Hummels. As always, I will be your MC for tonight's event. So thank you for joining us on this wonderful Monday evening in Los Angeles. Let's see. Our schedule for tonight is after a couple minutes of announcements by me, I will introduce our speakers. We will be joined, initially we will have a 15-minute or so talk given by Dr. Ethan Siegel, who will be talking about the first galaxies in the universe. Then we'll take some Q&A from all of you audience members through whatever medium you're watching this, either through YouTube or Facebook or Twitter. So you can type in there what your various questions are, and we will, I'll try and pick those out and ask Dr. Siegel. And so we'll do Q&A for about 10 minutes or so, and then move on to our next speaker, Sam Panada, who is a second-year PhD student here in the astrophysics department at Caltech, who's going to talk about magnetic fields in galaxies. I mean, who doesn't love magnetic fields? Magnets are awesome. So that should be super cool. And then we'll deal with 5 to 10 minutes of Q&A with all of you on questions relevant to Sam's presentation. And that should take us through about the first hour, and then we'll jump straight into pub trivia, astronomy-themed pub trivia. So this is an opportunity for all of you guys to respond to the questions that we give you about astronomy related questions and facts and trivia. And there will be a way that you can all interact through this website called Mentimeter that you just directly connect to, and there's no fees or no weirdness to it. You can just answer the questions that we lay out, and then it'll come up and we'll be able to see how everyone's doing relative to your peers. And that should take us to the end of an hour and 45 minutes or 2 hours. So feel free to come and go as you please, but I guarantee that it'll be an interesting night of science and astronomy for all of us. We do these events once a month. Our next Astronomy on Tap will be on Monday, May 23rd. It'll be given by Dr. Mike Wong, a planetary science researcher, and myself, actually. I'm going to give one of the presentations. He's going to talk about the science of Star Trek, and I'm going to talk about the science of Star Wars. And so we'll kind of discuss various things related to these science fiction universes and how they contrast and compare, as well as the relevant science and how close we are to those science opportunities in those universes. So that should be super cool. And then we also have a sister series of events called the Stargazing Lectures. The next one of those is May 13th. And that is given by Professor Katerina Hatziuanu, probably on gravitational waves, much like our last month's scheduled talk by Saul Tukolsky. But it will, I don't yet have the title for it, but I should have it out pretty soon. So I will keep you guys posted with all of that. So without further ado, let's get to tonight's program, and that Sam and Ethan, you guys want to jump in and join me?
Hey guys. Yeah, here we are.
Here we are. Welcome, guys. It's good to see both of you.
Yeah. Thanks for having me. Thanks for the invitation. You know, I'm not a Caltech local, and so it's kind of exciting to be able to come from the Pacific Northwest down to you guys, even if it's virtual.
Yeah. So you're in Portland area?
I am. I'm a little bit north of Portland right now and loving it up here by Mount St. Helens. We had our 3rd and 4th sunny days of the year this weekend. It was wonderful. It's rainy today.
Yeah, I remember growing up in the Northwest, and it was definitely the norm to have lots of cloudy weather, such that when I finally moved to Southern California and every day was sunny, I'd wake up and it'd be sunny. I'd be like, I got to get outside and take advantage of the day. And then it just happens all the time. And it's very different from up there, where every day it's sunny, you have to get outside and really, exploit that day for what it is.
Yeah. It's beautiful in its own way. And for those of you, most of you, I'm sure, are listening from Southern California, and Whatever you got down there, enjoy it as much as you can. I made it almost a full calendar year, 1 year living in Southern California, and that's almost enough for an entire lifetime for me. But if you love it as much as you can.
Yeah. Sam, where are you from originally?
Well, I grew up in Jamaica, so it's very sunny there.
Wow.
Yeah, so it's very similar to Southern California weather-wise.
Yeah. I suppose a bit more humid though, which sounds,
Yeah, more humid,
yeah,
more
sounds
rain,
pretty
definitely.
nice. That's cool. Cool, man. Well, yeah, thank you both for joining us. So our audience members, these Astronomy on Taps, part of the reason they're called Astronomy on Tap is because traditionally these were held in a bar or a tavern, and we were discussing this over beers. So I myself am having a humble sea beer from Santa Cruz that I got at a conference a couple of weeks ago. What Ethan, you look like you're drinking something tasty with that phone.
I've got a couple of things going on right here.
Oh goodness.
You know, I don't mess around when it comes to this. You say come to Astronomy on Tap, and I got to make sure that I'm ready for it. So in this hand, I have some tonic and lime, but the liquor it's mixed with is called Brennivin, which is the Icelandic national drink, and it is a spirit similar to gin, except it's made from something entirely different. So you'll have to figure it out.
Yeah.
And then over here, we've got a lovely little beer, which is a triple from New Belgium Brewery. And those of you who know New Belgium Brewery, I'm a good fan. This is a Belgian style triple beer and absolutely wonderful. So, you know, good thing I'm giving my talk first.
Indeed. Sam, any beverages for you?
I think I'm balancing us out tonight with just some water, my mug.
Good call. Teetotaling is oftentimes the solid way to go. So I commend you for it. Cool. Okay. Well, let's get started with the science tonight. Ethan, do you want to lead us off with your presentation? Do you want to share your screen?
Yeah, I'm going to figure out how to share my screen on the first try. Look at that. All right. So do we want to do an introduction?
Yeah, I was going to introduce you.
All right.
And then I'll let you jump into it. So, Dr. Ethan Siegel is an astrophysicist and science communicator. Some call him the greatest science communicator of all time, in fact. He's currently acting as a senior science contributor for Forbes magazine and Big Think. He earned his PhD from University of Florida with a focus on cosmology, is a former professor of physics and astronomy at Lewis and Clark College in the Northwest, and now spends his days writing stories, articles, books, creating podcasts and videos, and delivering talks to curious minds all across the world. He's won numerous awards for science writing, including the award for Best Science Blog by the Institute of Physics for his blog Starts with a Bang. And if you've never heard him speak or read his writings, you're in for a treat tonight. So I'm excited to welcome Dr. Ethan Siegel to tell us all about the first galaxies.
Yeah, and this is something that I'm really excited about because, you know, right now, here we are, we're looking out at the universe, and what do we see? We see things as they are today. It's one of the things that has always bothered me about the solar system. I like, how many planets were there when things first formed? We don't know. We only know how many are left today. When it comes to the stars and galaxies, how many of them have we had over our history? We don't know. We only have the ones we have left. But if we want to find the very first galaxies of all, that's something we actually have a chance at. So how would we do it? Well, you put your mind to it and you say, I know, I'm going to look. I'm going to go and I'm going to look and say, what do I do? You look and bam, there's the Milky Way up in the sky, easy to see. No. I need better tools than my eyes. So you say, oh, great, I'm going to build these big telescopes on the ground, a wide field, large aperture, capable of going deep. And you say, yeah, that's pretty good, but I can do better. And we do. So don't just look better. Look from space. Look where you don't have to contend with the atmosphere. Look in as many different wavelengths of light as possible. And what do you see? Well, you do see galaxies out there. You see galaxies in very different states of evolution than the Milky Way is. You see galaxies of all different types, of all different shapes, of all different ages. But what you do is you can do a third thing. I'm not just going to look, and I'm not just going to look better. I'm going to look for longer. And this that I'm showing you here is our deepest, longest view of the universe of all time. This little squared off section is known as the Hubble Extreme Deep Field, or XDF, a total of 23 days, 23 days times 24 hours. That's how much exposure time went into this one area of the sky. There are 5,500 galaxies in that region. That is 1/32 millionth of the sky. And even at that, when we ask, how far did that get us? How far did that deep, deep view of the universe get us? The answer is, even in that region of sky, we're only seeing about 10% of all the galaxies that we think are out there. Why so few? Well, because when we break it down, we say, you know what? At all these different distances, when I look out at that one region of sky as deeply as I can, I'm limited. I'm limited by a few factors, but the biggest one is that I'm not seeing the faintest galaxies, and I'm not seeing the farthest galaxies. And that's going to require us to overcome some obstacles. So let's focus first on what we do see. The first thing that we do see is over here at 0. That's a redshift of 0. That's galaxies that are like the Milky Way today. They are intrinsically red in color. They are big and massive. They have evolved complex structure in them. And they're relatively gas poor. They don't have a lot of material left in them to form new stars out of. But as we look farther and farther and farther away, we find that the galaxies we see are smaller, more numerous, less massive, have more gas, and are intrinsically bluer. And that's kind of interesting because you form stars in a big chunk all at once, and they're born of all these different colors, but it's the hottest, bluest, most massive ones that die first. So when you look at a galaxy and you measure intrinsically how red or how blue is it, that tells you how long has it been since it had its last big burst of forming stars. The problem is, no matter how far we look, we have 3 big things that are limiting us, that are keeping us from finding the first galaxies as easily as we'd want to. The first problem is this: the farther away something is, the fainter it appears. And the fainter something is, the harder it is to observe it. So this is just like putting a candle, a luminous candle, at a bunch of different distances. If I tell you I know how intrinsically bright that candle is, then if you can measure how bright it appears, you know how far away it is. The problem is there's a limit. However far away something is, there's a limit to how faint it can be, and we can still see it. So that's one problem we need to overcome, that the farther away something is, the fainter it appears. There's a second problem, that when something's far away, it emits light. That light has to travel to us. But the universe isn't just hanging around doing nothing. No, the universe expands. And an expanding universe means that all the light that's traveling through it, remember, light is a wave, and light's energy and color is defined by its wavelength. So as the universe stretches, the wavelength of that light stretches. And this is a big deal, because when you have a star like our sun, we know, okay, sun emits ultraviolet, visible, and infrared light. The youngest stars, the brightest stars, the bluest stars, they emit mostly ultraviolet light. And guess what? the universe expands so severely that what you can see, you can't really see it in the main image, and you can see it a little if you zoom in. And then at the bottom right, you see that real pixelated version. That is a very distant, very red galaxy. Intrinsically, almost all the light is ultraviolet. It's only the expansion of the universe that stretched the light from ultraviolet through the visible light into the infrared. So as the universe expands, not only are the most distant objects, not only do they look faint because they're so far away, they're also incredibly reddened by the expansion of the universe. In fact, that's the biggest limitation today on what something like the Hubble Space Telescope can see. It can only see galaxies to the limit of how far into the infrared Hubble can see. We have all sorts of observatories that use all sorts of filters on their light. Here is a mix of, these are the filters that the LSST, the Large Synoptic Survey Telescope at the Vera Rubin Observatory has. This is a mix of ultraviolet visible light and infrared filters. But with our atmosphere and everything, we can still only see a little bit into the infrared. If you want to see farther into the infrared, so you can see things that have been stretched even further by the expansion of the universe, you need a new observatory. So those are two problems. Far away things are, the fainter they appear, and the more light you need to gather. Second problem, the farther away things are, the more the light gets stretched and redshifted by the expansion of the universe. And there's a third problem. The third problem is there is stuff in the way. This is, believe it or not, the same object. This is what's called a Bok globule, which is named after Bart Bok, and it's just a cloud of neutral gas. This specific one is called Barnard 68. On the left is what it looks like in visible light. On the right is what it looks like in infrared light. And this is amazing. This is amazing. The things that are invisible because neutral matter will block the light, invisible light, you can actually see them in infrared light. I'm going to show you a couple pictures. This is a view of the Milky Way galaxy. This is a view taken by the European Space Agency's Gaia satellite, currently active satellite, working to measure all the stars in the Milky Way that it can and determine what is their distance, what is their three-dimensional position, how are they moving, what's its parallax, etc. Great observatory. But when you look at this, look at all that dark stuff in there. That's neutral matter. That's neutral matter blocking the starlight in back of it. Starlight comes from behind it, runs into this neutral matter, gets absorbed, and you can't see it. But if I took the same galaxy and instead of looking in visible light, I were to look in infrared light, look at that. Now I can see everything. The infrared starlight shines right through the dust in the galaxy. The dust in the galaxy doesn't absorb it. It just passes right through. In some wavelengths of light, in the mid and far infrared, I can even see the warm glow of gas. This is multicolored because the blue is the near infrared light and the green and red is the far infrared light. So this is a composite image. And what this means is if I want to see farther, what I need to do is not get that ultraviolet light that was red shifted into the infrared. What I want is that initial light. Because remember when we looked at this, you saw, back when we were making the first stars and the first galaxies, there was still all this neutral matter in the universe. It takes starlight to ionize that matter and make it transparent. So if you make ultraviolet light, you can't see it. Even if you build a good thing that can observe that redshifted light, you need light that was emitted in the infrared. So it already went through that dust and then gets redshifted into the mid-infrared, and you need to still be able to see it. So how are we going to do that? Well, those are the limits of Hubble. Hubble, we've seen as far as something like Hubble will ever be able to see. We might get lucky and find a place where Hubble hasn't looked, where there happens to be a galaxy a little bit more distant than the current most distant record holder. But that's not going to get us back to the very first galaxies. If we want to do that, we need a bigger observatory so it can see fainter things. We need something that can see farther into the infrared than Hubble can see. And we need stuff that can see through the neutral matter that's in the way. And that's part of the reason we built the James Webb Space Telescope. It is bigger, it is colder, it is designed to see farther into the infrared. And I want to draw your attention to this upper right corner of this slide here, where I've got a little graph. If I were to put Hubble in here, right? Let me see if I can do, how do we do this? I should be able to draw on this. So let's see if I can draw stuff. So if I were to put Hubble on this graph, it would be somewhere like right around here. That Hubble can get us down to about here. And that's as far as Hubble can see. You have other observatories. WISE is up here. Spitzer was over here. Herschel was out here. But James Webb is these points here. The James Webb Space Telescope is going to be able to see fainter things at longer wavelengths than Hubble or any observatory was ever able to see. And that is our big clue. That's our big clue to what's coming next, because here is the current record holder. This is a galaxy named GN-Z11, and it comes to us from when its light was just 400 million years after the Big Bang. That is behind where most of this neutral matter exists. It just happens that it is located along what we call a serendipitously reionized, which means there's only a little bit of neutral matter, line of sight. What we know, though, is as we start looking at the sky with the James Webb Space Telescope, this is the current deepest view we have from Hubble. And this is the view we're going to have from James Webb. So from the Hubble view of a region of the sky to the James Webb view, and you notice that different features stick out because it's able to reveal early red galaxies that Hubble can't see. And we're going to look at a very large piece of the sky. The dream, the way we'll know we're seeing some of the first galaxies of all, is because of the type of stars we'll find inside. Right now, we have a population of stars that's very much like our sun, right? When we see a star like our sun, astronomers give it a very creative name. We say, oh, that's a population 1 star, because the sun is the first type of star we found, and there are a bunch of stars like it. Population 1 stars are rich in heavy elements that were made in stars over and over. They can have rocky planets around them. They come about at late times in the universe, and they're great candidates for having life around them. Population 2 stars were formed earlier. There were fewer generations of stars that came before them. They're mostly poor in metals. They're made mostly out of hydrogen and helium. But in theory, there's a third type of star, a population 3 star, made out of truly pristine materials, just the hydrogen and helium that was left over from the Big Bang. That is like the dream of James Webb. The community is split. They're arguing, is James Webb going to find any population 3 stars? We don't know. It's part of why we're looking. But if they do, that means when you see that, you know these are stars that are being made for the very first time ever. And we just might find galaxies that have population 3 stars in them. So if you want to find the farthest, earliest, very first galaxies, how do you do it? You look for faint, reddened light. You look in the long wavelengths so that you get light that was emitted in the infrared that you can still see even after the expanding universe has expanded it. You want to look for long times because the longer you look, the fainter you can see. You want to see as faint as possible. You need to look with the right tools, which in this case is going to be James Webb Space Telescope's MIRI, the mid-infrared instrument. And finally, you want to look for only pristine stars. If you see stars that have been through many generations, you're like, okay, I'm seeing an early galaxy, but it's not the very beginning. I want it to be earlier. Well, we have that observatory. We have the James Webb Space Telescope. Hopefully, many of you got to enjoy its Christmas launch. And hopefully, the next time you hear an announcement about we found the new farthest galaxy ever in the universe, it won't be because someone found a candidate farthest galaxy in the universe without spectroscopic confirmation, which somehow people still report like that's news. No, you want to find something that you know is more pristine and older and farther than anything else we've ever seen before. And right now, with the tools we have in orbit that are being calibrated, I would be shocked if a year from now, this galaxy, GNZ11, was still the farthest galaxy in the universe. So now you know how we're going to find the very first galaxies of all. And maybe the next time you hear someone talk about this, we will have a brand new cosmic record holder.
Excellent. Thank you. Thank you, Ethan. That was wonderful.
That's great. I'll imagine there's some sort of applause.
It's like a stadium of everyone just shouting and cheering your name. Seagull, seagull.
Wow.
Yeah.
Wow. Well,
that's the best I can approximate.
I appreciate it. That was full of effort. I like it.
You'd like the sitcom reels for Zoom, Cameron.
That's right. Yeah. There were a bunch of questions from our audience, so I'll try and relay some of those to you.
All right, we'll go through them as fast as we can.
Let's see. There was this one from Abhinay Pathareddy. Are the images we collect via telescopes corrected or optimized using software at all? In essence, are telescopes just large DSLRs with little or no software improvements, or do we already do some sort of image improvement using software the way perhaps iPhones or something like that do?
You know, this is part of why you have pipeline data scientists who work on the telescopes, because, you know, you would love to say like, oh, I just want the raw data, right? I just want the raw data. A lot of times the raw data you get for a telescope is unfit for scientific analysis because there are specifics that go on with each telescope and each observatory. So there are actually real people scientists who deal with the direct data products so that they can take this data, do the necessary cleaning. This is obviously a little more complicated for ground-based telescopes than space-based telescopes, but they have scientists on all instruments who work with this that are going to say, okay, look, we know that was a cosmic ray, we're going to remove it. We know that was, you know, various things can come up that will pollute your image. So what they do is they work to give you data products that are usable, that you can get usable scientific data from. And that's when you download a public image file from that, you are getting the already once passed clean data, not like optimized from an iPhone, not like you heard in like the Kyle Rittenhouse trial, which, wow, I have opinions on that we're not talking about here. And that is the answer to your question. Not iPhone level clean, but basically you want to think about what the job of those people do, those astronomers do, is they correctly calibrate the data, because there's nothing worse than incorrectly calibrated data. That's how you draw bad conclusions from bad data.
I believe that in the end, what gets released, because all the data that's taken by Hubble or the James Webb gets released to the public. And I think both the raw as well as the, as you're describing, the processed data that isn't like totally messed with too much. It's calibrated and that sort of thing. I think both streams of that get released to the public so they can use
Yeah,
it.
I mean, if you want to think you can do a better job than the people who work on the telescopes, and you think you can calibrate the data better, what do they say in Australia? Go for your life.
Scam Assassin asks, what kind of resolution can we expect the James Webb Space Telescope to see for these first galaxies? Because you showed I liked your final kind of fade back and forth between the HST, the Hubble Space Telescope image, and what James Webb would see in terms of the infrared versus optical. But do you happen to know how much higher resolution we'll be able to? I guess it's specific to the instruments like MIRI or
right. So there's this thing, right? In general, it's just angular diameter. You say, how big is my telescope? And that determines the resolution you can see. So you say James Webb's bigger than Hubble. That's great. But it's a little different because they're looking at different types of light. The resolution of your telescope is not just how big is your primary mirror, it's how many wavelengths of the light you're looking at can fit across your primary mirror. So James Webb is going to have a very different resolution for what it can see at 500 or 600 nanometers, which is the shortest wavelengths it can see, versus what it can see at about 30 microns, which is 30,000 nanometers. So there's a wide range of how well resolved James Webb can do. At its optical wavelengths, it can do about, it can do about 250% better than Hubble can do. But at the farthest, it's going to be maybe 15 times worse than Hubble is. For the farthest galaxies of all, honestly, I'd be happy with 1 pixel. With 1 pixel, you can do so much. But because I'm betting you that most of the galaxies that are the most distant that James Webb is going to find are going to be gravitationally lensed, which means there is a mass source and the background object, the background light is coming from behind that. That light will get curved around by the mass, magnified, and stretched. And when it gets stretched, what is just a tiny object on the sky can actually take up a whole arc, make up lots and lots of pixels. So I'm betting that that's what we'll see from James Webb, is actually a lot of these arced galaxies will be the most distant ones we find.
I agree with you. I think it'll be really interesting to see some of these gravitationally lensed guys. Another question, EatNato1 asks, why are the earliest stars bluer if their light has been more redshifted, if they're farther away from us?
It's a good question, right? So when we talk about something being red or blue, you'll notice I kept throwing this word intrinsically or apparent in there because there's 2 things. One of them is you say, okay, I'm going to correct for the redshift. And the way you do that is you say, okay, quantum mechanics works the same everywhere in the universe. Electrons exist in atoms and ions, and they go up and down in energy level. And when they go down, they emit light of a very specific wavelength. So I'm going to measure these emission lines, or opposite, I'll measure these absorption lines. And if I can match them up to what element did they come from, then I know, oh, that's how far away that object is in terms of redshift. So I know how much that light has been stretched by the expansion of the universe. So then I do a little bit of theoretical astrophysics known as division, and I divide that out. And then I say, oh, okay, well, that's the intrinsic light. Like, here's the light I observed. What does that mean for intrinsically? And then what I always find intrinsically is the younger my galaxy is, the closer to the beginning of the universe it is, the bluer the light overall is. One of the fun things about why the very first stars will be super, super blue is because when you make stars, you make stars of all different masses all at once. Today, both population 2 and population 1 stars have enough heavy elements in them that the heavy elements cool the gas clouds. So smaller mass things can collapse and make new stars. In the early universe, back when you're making population 3 stars, you only have hydrogen and helium. So what of all the ways you can have hydrogen and helium, how do they radiate heat away? Well, guess what? Of all the ways they can combine, it's molecular hydrogen, H2, which is pretty rare in space. That's the most efficient cooling thing. So instead of today, where the average star is about 40% the mass of the sun, our calculations tell us the average mass of the first stars is about 10 times the mass of the sun. So instead of living for tens of billions of years like our sun does, these earliest stars only lived for maybe 10 or 20 million years before they died. So if we're lucky enough to find them, they're going to be really intrinsically blue, but they're going to look super infrared because that's all we can see.
Excellent explanation to a tricky question.
They always try and trick you. You just have to bring everyone along for the ride.
A couple more questions. When do you predict we will be, Jasenia Colon asks, when do you predict we will be able to receive images from the James Webb Space Telescope? I think they've announced this, that the first images released will be June? Is that right?
So this was the original timeline, right? The original timeline, they said, we're going to deploy it, and then we're going to see how things are going, right? It takes time for the instruments to cool down. It takes time to get the calibration properly. It takes time to make things properly aligned. And so they were going to be conservative about it. And they said, look, we're going on a 6-month timetable here. I've got to say, I've been really impressed. If you've been keeping up with them, they're actually a little bit ahead of schedule.
Yeah, they've been doing super well.
June is the safe bet. You will see the first fully calibrated, cooled, and properly equipped James Webb images at the end of June at the latest. I wouldn't be surprised if we didn't start seeing some of these maybe 3, 4, 5 weeks earlier than that. So, come back at the end of June and you'll definitely have them. But I wouldn't be surprised if NASA and the James Webb Space Telescope science team and the people at Space Telescope Science Institute didn't give us a little bit of better than expected with that.
Yeah, I think you're right. Just a couple last questions before we move on to Sam's presentation. Andrew Reidemeyer asks, question, would the earliest galaxies have shared matter with each other at a high rate through collisions and cannibalism, or were they fairly stable from the start in the early universe?
All right. So right now, I can only answer you theoretically, because what haven't we done? We haven't found the first galaxy. So in theory, back when the universe was smaller and more uniform, but also expanding more quickly, this is a giant cosmic race. What's the race? The expansion of the universe versus gravity. And the way gravity works is, on some scales, gravity can win. It wins on the smallest scales first. So the very first stars that form shouldn't be in galaxies at all. They should just be these individual star clusters that form. They go off like fireworks and they enrich the medium around them. And then some things will fall back, or maybe it'll trigger new waves of star formation. The first galaxies that we get should actually come about when you have these larger clumps of mass that draw star clusters into them. And so the very first galaxies that form should be formed from the merger and accretion of smaller structures. And over time, we expect galaxies to grow and grow and grow through mergers, accretion, and, as you said, cannibalism, because galaxies are cannibals. That's what they do. They eat each other. They eat their brothers. They eat their sisters. They eat their parents. They eat everything. Gravitation is this runaway force that never looks back. So what we expect the James Webb Space Telescope to teach us, right? Hubble has shown us what the universe looks like. James Webb is going to teach us how the universe grew up. And that is the biggest advance we're going to get. I'm telling you what I expect the story to be. And by I mean, like what the majority of scientists working in the field expect it to be. But part of the reason we look is not just because we want confirmation of what we think, it's because we want to give the universe the opportunity to surprise us, because it has surprised us in the past. It no doubt will surprise us in the future. And when it does, that's when we're going to learn the most exciting things of all. Because I can tell you what I'm confident James Webb is going to find, but I guarantee you it's going to be much more exciting, the things we weren't expecting to find that are actually out there.
Great response. That's very good. You are one of the greatest science communicators of all time, it turns out.
Yeah, it wasn't just hype. Wasn't just hype.
Final question is Ananda Ganguly asks, in science writing, do you find yourself having to make a trade-off between understandability versus scientific rigor? And if so, how do you strike a balance between those two kind of extremes?
No, I don't trade it off, because I will not trade off the scientific accuracy. So if you want something to be understandable, you have to understand it well enough that you can explain it in the 1,000, 2,000 words, whatever you're going to take to do it. If you can't explain it that well, if you can't explain it that concisely, then you shouldn't be explaining it yet. You have to figure out how to package that in a way people can understand. That means remove the jargon, keep the concepts, and make it so you start out where everyone's comfortable. And each new thing you introduce is one step, not a giant leap, it's one step. So if you followed me here and we take this step together, you can be okay here. And if we do this a few times, then by the end, you're going to be where we need to be. So I think, look, if you're lazy, if you're a hack, if you're not very good at your job, or you don't know what the hell you're talking about, yeah, that can be a big problem. But part of the reason that I think it's important because it's important to do both of those things. You want to be understandable. If you're not understandable, what are you doing as a communicator? And also, if you're cheating the concepts, if you're making things simpler than they ought to be, then what are you doing? You're just misinforming people under the guise of science communication. So my advice is, if you're going to do science communication, do it at a level where the things you're communicating come across clearly and understandably at the level of depth you're willing to go into. I'll tell you one last brief story. They made in 1980, before most of your times, I bet, United States men's hockey team won the gold medal at the Olympics. This was called the Miracle on Ice. And a few years, right, they beat the Soviet Union. Crazy bunch of amateur kids beat the Soviet Union. And then they played the gold medal game against Canada, where hockey is like second nature. Kids learn to play hockey before they learn to crawl. And what happened? They beat Canada in the gold medal game. They went to make a remake of this movie about 15, 20 years ago, and they called the movie Miracle. And they were like, who are we going to get to play these hockey players? Are we going to get hockey players and teach them how to act, or are we going to get big name actors and teach them how to play hockey? They went with the hockey players. Why? Because they said it's easier to teach hockey players how to act than it is to teach actors how to play convincing hockey, because you need to play hockey your whole life to be any good at hockey. Otherwise, people can tell, like, oh, look at it. He can't even skate. He thinks he's playing hockey. He can't even skate backwards. What's he doing? So I would say, if you want to go for the most difficult things, the most important thing is that you know your physics. You know your physics, you know your astrophysics, you know whatever it is you're going to talk about. Only then do you have a hope that you can break it down and learn the communication skills. To go the other way, to be like, well, I'm a great communicator and I don't need to know the science. As soon as you leave that first prepared question, as soon as someone asks you about any detail, you're going to be dumbfounded. So I think there is an untapped market of people with the expertise and the communication skills to do a good job of this. And for me personally, that's the niche I'm trying to fill as best as I can. So anyone wants to come and help me out, I could use the help.
Sounds great. Well, I think you're doing a great job thus far. So thank you. Thank you, Ethan. Cool. Okay. Well, let's move on to our second speaker for this evening. Sam, do you want to share your screen and I'll give you a quick introduction?
Yeah, I can do that.
Okay, awesome.
After Ethan's closing remarks, I feel like I have very big shoes to fill now. Is it looking okay?
Yeah, it looks great. Looks perfect. Okay. Sam Panada is a second-year PhD student at Caltech, using supercomputer simulations to explore how magnetic fields can influence the formation and evolution of galaxies. He obtained his BS in physics and astronomy and BA in mathematics, both at the University of Iowa, where he was a Latham Fellow in Science Engagement. Sam is passionate about making astrophysics accessible to the public and promoting diversity, equity, and inclusion in the field. In his free time, he enjoys hiking, climbing, and playing tennis. Oh, I didn't know you liked playing tennis.
Now you know.
Now I know. Awesome. Okay, I'll let you take it from here, Sam. Thanks.
All right. Yeah, thanks for the introduction, Cameron, and thanks for the great talk, Ethan. So yeah, today I'll be talking a little bit about why astronomers or astrophysicists care about magnetic fields in galaxies and how we actually measure them. And so I'll start off talking a little bit about the basics of magnetic fields, especially astrophysical magnetic fields. And first thing I want to say is that magnetic fields are generated by moving charges. And one magnetic field that we're all very familiar with is that of Earth's. Earth's magnetic field is generated by these churning and swirling motions of charged material in the Earth's outer core, which is filled with liquid molten metal. So it's filled with charged particles. These motions, in conjunction with the Earth's rotation, set up currents which amplify and sustain the Earth's magnetic field. And this is a phenomenon that we like to call a magnetic dynamo, which just refers to the conversion of kinetic energy to magnetic energy. So while galaxies are not really filled with liquid molten metal like the Earth's outer core, much of the gas in galaxies is highly ionized, meaning that there are large numbers of free charged particles moving around, which generate currents and so also generate magnetic fields. And these fields have been thought to be amplified from very weak fields in their universe's early history by similar dynamo processes to that which occur inside the Earth's core. So here on the right, I'm showing an image, a beautiful Hubble Space Telescope image of M51, the Whirlpool galaxy. And overlaid on this image are streamlines showing the structure of the magnetic field, which I'll talk a little bit more later in the talk about how we actually infer. So why do astrophysicists care about these magnetic fields? So I've told you that these exist in nature and throughout the galaxy, throughout every galaxy, but you may be asking why we care. Well, one reason is that the physical evolution of galaxies is tied into the formation and evolution of its primary constituents, which are stars. And stars form by the collapse of very dense balls of gas that is magnetized. And magnetic fields act in such a way that as gas is collapsing, they want to resist this compression. And so if you have a ball of magnetized gas that's collapsing to form stars, magnetic fields work to slow down or prevent this collapse. And so magnetic fields can play an important role in influencing the dynamics of star forming regions. And so they can change the star formation rates of stellar nurseries. And here I'm just showing one of these stellar nurseries, the Cat's Paw Nebula, NGC 6334, which this is an image taken with the Spitzer Space Telescope in the infrared. So another reason that we care about magnetic fields are that magnetic fields are like railroad tracks. When a star goes through its lifetime, it eventually dies in a very violent explosion that we call a supernova. And when this happens, they release a lot of energy, and they release a lot of energetic charged particles into the galaxy. And since these particles are charged, they feel a force from the magnetic fields that are threading the galaxy that determines their motion. So magnetic fields are like the railroad tracks for these highly energetic charged particles to travel throughout and around galaxies. And these cosmic rays, which is what we call these charged particles, carry a lot of energy, which can significantly influence the motion of gas within and around galaxies. So we've established that magnetic fields in and of themselves can influence the dynamics of gas on physical scales relevant for star formation, and that they can also provide rails for these cosmic rays to propagate throughout the galaxy. But one of the biggest questions in our understanding of galaxies is the question of why they stop forming stars. And recently, astronomers have been really interested in the gas which surrounds galaxies, which we call the circumgalactic medium. And this is one of my favorite figures from a review paper a few years ago. So this is just an artist's sketch of a galaxy and the surrounding gas, which we call the circumgalactic medium, which here you can see these outflows coming out of the galaxy and falling back on. And then it's also surrounded by this diffuse gas shown in purple. So it turns out that cosmic rays can provide a substantial source of pressure, which drives gas out of galaxies. I think this movie is not playing. Is it playing?
No, it doesn't look like it is, unfortunately. Do you want to go back and forth, like go to the previous slide and maybe it'll start, or? No, it doesn't seem to be.
The sad thing is it played in reversal.
In our test,
played in rehearsal, Sam.
The saddest part is this is one of my movies.
Let's just go full, out of full screen for a second. Because I want it to work. Let's see. Oh, there it goes. Okay.
There you go.
So it turns out that cosmic rays can provide a substantial source of pressure, which drives gas out of galaxies. And this can keep gas from falling onto the galaxy, depriving galaxies of the fuel for star formation. So here I'm showing a movie of simulations from the FIRE collaboration, working with the group I'm a part of. This movie is actually made by Cameron, who is our host tonight. And in the top panel, it's showing a simulation of a galaxy that doesn't include cosmic ray physics. And the bottom panel shows the same galaxy, but with a simulation that now includes cosmic ray physics. And what we see is that without cosmic rays, outflows are quite chaotic and unstructured. Whereas with cosmic rays, we have a more stable, coherent, steady outflow from the galaxy, which can more effectively keep cool gas, which is the fuel for star formation, from raining back onto the galaxy. And so since magnetic fields are the rails on which these cosmic rays travel, magnetic fields are crucial to understanding how these cosmic rays propagate, and how these cosmic rays can influence the evolution of galaxies. I'm gonna go full screen again. And so we can't see magnetic fields, even though I've talked about how important they might be. So how do we actually measure them? Well, we've measured magnetic fields in interstellar gas from magnetometers aboard the Voyager spacecraft, which just left the boundary of the solar system a few years ago. And they were launched, 40, 50 years ago. And this is the only direct measurement of magnetic field strengths we have anywhere in the galaxy. And that's not very far from us. So as astronomers, we have to get creative about the one thing that we have in our toolbox, which is how we're going to use the light from stars and galaxies. And so one of the properties of light that doesn't often get discussed much in your typical physics class is polarization. So light is described by a wave, which has a direction in which it propagates, as well as a direction in which it oscillates. And so we call the plane in which the electric field of this electromagnetic wave oscillates the polarization. And so you might be familiar with this concept if you've worn polarized sunglasses while driving on the highway or in a bright outdoor environment, for example, in a snowy area. So light from the sun is unpolarized, but when light reflects off of a very bright surface like snow or a road, it imparts a polarization which we perceive as glare. So if you wear polarized sunglasses, they work to only let one polarization of light in so that you don't see this glare and don't get blinded while you're driving or hiking out in the open. And so we use polarization to infer magnetic fields because there's interstellar dust which polarizes the light. So in space, there's a lot of very cold dust which is created from the death of stars. And these dust grains are not spherical. They're kind of like little tops. And they align with magnetic field lines in a way that their short axis is parallel to the field. And so if we look towards an unpolarized light source, like a star, the foreground dust, which is aligned with the magnetic field, absorbs this light in the optical and re-emits it in the infrared since it's so cold. So when we look at this unpolarized star in the optical, the transmitted optical polarization tells us about the magnetic field direction in the plane of the sky. And when we look in the infrared, we can see the polarized infrared emission emitted by these dust grains as well. So this tells us about the direction of the magnetic field in the plane of the sky. And so we can use this to make some very beautiful visualizations of the magnetic field structure in both our galaxy and other galaxies. So this is an image, or this is a visualization of data taken with the Planck Space Telescope, which looked at infrared emission in the galaxy. And so this is a map showing the streamlines of the magnetic field in the Milky Way as inferred from the polarized dust emission. And you can see all this structure and curvature in the magnetic field that we infer from the dust polarization maps. Similarly, we also have observations of other galaxies. So this is M51, the galaxy I showed earlier in the talk, with the streamlines here, which are determined from dust polarization observations as well. So we've talked about using dust polarization to determine the orientation of the magnetic field in the plane of the sky. But what about the magnetic field direction along the third dimension in our line of sight? So here, astronomers utilize a property of magnetic ionized gas, which is called Faraday rotation. So as light waves pass through magnetized ionized gas, there's an interaction which causes the plane of polarization to rotate dependent on its wavelength. And if we have a signal or a burst of light that's periodic, for example, if we look at a pulsar, which sweeps out periodically like a lighthouse, the ionized gas also causes the signal to disperse in time. So if we look towards a bright, intrinsically polarized source, for example, a neutron star or pulsar at two different wavelengths or frequencies, we can determine the Faraday rotation and the dispersion measure, which together tell us about the average strength and direction of the magnetic field along our line of sight. And when we do this in the galaxy, so this is a recent study which compiled over 1,000 sight lines towards pulsars within the Milky Way, and this is the resulting map of the rotation measure that they get. And so this is telling us about the structure of the magnetic field along our lines of sight towards these pulsars. It tells us both about the strength and the direction. And so we can see that in the galaxy, there's a lot of structure, both on small scales with reversals in the sign, and also on large scales. And another method that we use to measure magnetic fields is through the same cosmic rays that we are so interested in the physical implications of. So while these cosmic rays whiz along their helical paths in galaxies, they also emit radiation, which we call synchrotron radiation. And this radiation is intrinsically polarized. As these cosmic rays orbit along field lines in the plane of the sky, their circular path traces out a polarization towards us. And the intensity of this radiation is also dependent on how fast these cosmic rays are gyrating around the field lines, which is also dependent on the strength of the field. So from the intensity of this radiation, we can learn something about the magnetic field strength. And from the polarization, we can learn something about the direction of the magnetic field in the sky. And so here is a map of magnetic fields around the halo of a spiral galaxy, NGC 4217, as inferred from synchrotron emission. And so the main takeaways that I wanted to express today were that magnetic fields might be very important for the dynamics of gas in galaxies, both from the smallest to the largest scales, and that cosmic rays are interwoven with magnetic field lines, which motivates and informs our understanding of these magnetic fields. And we can determine the directions of magnetic fields in the galaxy and in other galaxies through polarization due to dust. We can also determine the strength and direction of magnetic fields along our lines of sight through the concepts of Faraday rotation and dispersion measures. And finally, synchrotron radiation from cosmic rays gyrating around magnetic field lines can tell us about the direction and strength of magnetic fields, both in our galaxies and in others. Thanks.
Excellent. Thank you very much, Sam. That was great. So yeah, I encourage, the crowd goes wild. I encourage audience members to ask questions in your respective kind of chat boxes that come back to me, and I'll ask them of our speaker. There have already been a few. Let's see. So Andrew Reitemeyer asks, due to the lack of rotation, I assume elliptical galaxies have only weak magnetic fields, or is there some more, something more complex going on there?
Yeah, so that's a good question. So the dynamo effect does not solely depend on rotational motions, but it can also be caused by turbulent motions. And so in elliptical galaxies, if they've had long histories of very chaotic turbulent gas motions, you would expect to find similar magnetic field strengths to spiral galaxies that are rotating in a coherent manner.
So can you explain, just in case the audience doesn't necessarily understand what turbulence is in the context of all of this, what that means and how it contributes to like the dynamo and all of these sorts of things? Yeah,
so if you have a bunch of charged gas and it's rotating versus it's moving around very chaotically, so there's two different kinds of dynamo effects. So one is driven by this rotational motion, and one is driven by these chaotic random motions, which we call turbulence. And so if you have a very turbulent distribution of gas, you can find that magnetic fields amplify similarly to how they would amplify if you had like pure rotational motions. And actually the time scales over which the fields get amplified is different. And it's very rare that a given dynamo only has one or the other. They typically have a combination of both. So different dynamo processes will dominate on different time scales.
I guess related to that, when two galaxies merge, because as Ethan was talking about in his presentation, galaxies are cannibals. They're constantly consuming their neighbors and growing through this accretion process where they grow that way. Does that enhance the magnetic field strength as well because of it induces this rotation, or it induces turbulence so is it just like a linear growth pattern where in the early universe there weren't magnetic fields, or the magnetic fields were really, really, really low, but over time through their growth they just build because of accretion, or build because of turbulence, or build because of, I don't know, some other processes?
Yeah, it's actually a very open question that people are just really getting to look at in the past decade or so, because it's only been in the past maybe 15 years that these simulations that we use to make these theoretical predictions have been able to include the physics of magnetic fields. And so it's a very open question, and also subject to constraints from future observations, how these magnetic fields actually do get amplified from the earliest stages of the universe, whether it is, just a galaxy doing its thing, rotating and having amplification due to things happening within the galaxy, or if it's because of mergers or environmental effects. I think these are all very relevant and current questions when it comes to magnetic fields in galaxies.
Someone you might be surprised by may or may not have written their PhD thesis on that topic too.
Oh, really?
Yeah, about where the seeds of these magnetic fields in galaxies come from, and whether they can originate from the pre-recombination universe, or whether they have to be created at later times via something like the Biermann battery or stars.
Oh yeah, so you worked on magnetogenesis. That's cool.
I did.
So was it what was your conclusion, that it was
the
Biermann battery, or?
You inevitably do form seed magnetic fields at the epoch of recombination, and they do get frozen in to the universe. And they're small seeds, about 10 to the minus 24 Gauss, but gravitational collapse is real, freezing in is real, and dynamo amplifications are real. So there are really three candidates for the origin of these magnetic fields in galaxies, and the plasma dynamics of the early universe, the Biermann battery in the pre-star formation universe, and stars that you form once you form stars are all viable candidates for where they come from. And it will take a more comprehensive quantitative analysis that maybe Sam will figure out for us.
Excellent. Excellent. Cool. Okay, so a few more questions from the audience for you, Sam. Do the magnetic fields in galaxies affect the motions of stars in a spiral galaxy, or is it just dictating the motion of the gas as you were describing?
Yeah, so it wouldn't influence the motion of stars because that would be mostly dominated by gravity in the galaxy. Yeah, magnetic fields don't have any effect on the motions of.
They're super, super low intensity, so that the stars are just like pew and don't. It's like a cobweb for a freight train or something like that, right?
Mm-hmm. And also, yeah, the charge of the sun is like extremely small because it's got equal numbers, almost equal numbers of electrons and protons. So yeah, it's if you actually worked out what the force the sun would feel due to some interstellar magnetic field is, it would be extremely marginal. Yeah.
Okay. Yeah, that makes sense. Yuri Young asks, similarly, related to what you just said, does the magnetic field of the galaxy affect us in our solar system or even on Earth? Because a lot of people have some sort of intuition with which, the Earth is affected by the sun's magnetic field in terms of aurora and the northern lights and all of these sorts of things. So how does the galaxy's magnetic field kind of play into our solar system?
Our solar system. So it doesn't really have an impact on our solar system per se. So the relevant magnetic fields on Earth would be first and foremost the Earth's magnetic field, and after that the effects from the sun. But the only relevance would be perhaps, like I mentioned, the Voyager constraints on interstellar magnetic field lines. So we can only measure those once the Voyager spacecraft left basically the region that's kind of shielded off by the sun's magnetic field lines. And so we knew that Voyager is in interstellar space because we passed this sort of termination shock of where the sun's magnetic field kind of meets the interstellar galactic magnetic field. And so that's how we know kind of where the distinction is. But we don't actually, on Earth, have any real effects of the galactic magnetic field. Although one thing is that we do detect cosmic rays on Earth. And this cosmic rays propagate all throughout the galaxy, and they're, moving along field lines, scattering off field lines, doing all sorts of crazy motions. And when we measure those, we don't really know where they came from because they've been traveling throughout the galaxy. And so that is one way in which the galactic magnetic fields are kind of influencing Earth, is that we get hit by cosmic rays from all over. And luckily, the Earth has a magnetic field which shields us from many of these cosmic rays. And so we have life on Earth. Whereas if you're on Mars, doesn't have a magnetic field, or not Mars, if you're on a planet that doesn't have a magnetic field, you're subject to all of this ionizing radiation that might make it more inhabitable for life.
That makes sense. Where are the magnetic fields of our galaxy most concentrated? Is it at the center? Because I think, again, people have, this was asked by Wei Sensei. Because I think a lot of people have this intuition of, like, for instance, a bar magnet, and you've got your field lines coming out from that bar magnet. So in our own galaxy, which is more distributed than a single solid structure like a bar magnet or a kitchen, a refrigerator magnet, you don't necessarily have that kind of singular magnetic field structure that's dictated by a single structure that's emanating from a single structure, or do you, or is it spread out through the entire galaxy and the gas and the material composing it?
Yeah, and part of this is also like we're trying to also figure out the geometry of the magnetic field in galaxies, but there have been studies which have shown that, so in terms of regions where the magnetic field is stronger, in molecular clouds, the gas is so dense that as it's so dense, the magnetic field lines are also closer together. And so that means that the magnetic fields are stronger. And so if you want regions in the galaxy where magnetic fields are very strong, place to look would be molecular clouds. It has been shown that molecular clouds closer to the galactic center do have stronger magnetic fields than ones further away from the galactic center, but it's not known whether this is a universal phenomenon or if there's some, if it's just a spurious thing.
And then finally, a question that was asked a few minutes ago by the Nerdy Walker. What role did magnetic fields play in the formation of the earliest galaxies? I guess we've kind of discussed this a little bit with Ethan's contribution from the early universe and how things were really low level, but kind of built up. But did they play more of a role in the early universe than today? Or is this still open?
So my intuition would be that they didn't play much of a role in the early universe. For one thing, they were so weak, and magnetic fields took a lot of time to amplify cosmologically. But on the second thing, the very early stages of galaxy formation are very much dominated by the force of gravity. And this is something that we understand from both simulations as well as our first order observations that test our theories and simulations. And so the magnetic fields may play more of an important role later on in a galaxy's lifetime, where we're concerned more about why a galaxy might be moving from one that is actively forming stars to one that's not.
Okay, makes sense. Excellent. Well, thank you, Sam. That was great. And you as well, Ethan. So now is the time during Astronomy on Tap when we switch to the pub trivia, where all of our audience members are encouraged to contribute and submit their answers. One quick note is that unfortunately there are no prizes for pub trivia, unlike a standard pub trivia where you might get like, I don't know, a bag of Cheetos or a beer or something like that. I can't ship those to all of you. So what this means is that your primary prize is just to have fun and to enjoy it and learn something. But it also means there's little incentive for you to cheat, even though you have literally at your fingertips all of the world's knowledge at your disposal. Try not to look up the answers because, I don't know, you're only cheating yourself. I'll channel like my fourth grade teacher. You're only cheating yourself. So let's see if I can share my screen and do this whole business. All right. I will present. So can Sam and Ethan, can you guys see this okay?
Looks
all right,
good.
so,
Astronomy on Tap, Los Angeles.
Yes. So audience members, I encourage you to go to this website called www.menti.com. There's no cookies or pay thing, or it's not going to start spamming you with anything. It's just a way that we can interact. And you can answer the questions that I throw up here on the screen. So if you go to that website and then you type in this number 8638-7511, you'll be able to answer the questions as they pop up through here. So I encourage you to do it. It's pretty fun. And like I said, there's not really anything to be gained from cheating and knowing the right and getting the right answer if you look it up. So I encourage you to answer with your best guess, or maybe throw in a comical guess. That's what people do in real pub trivia, is when they don't know the answer, is make up a funny response, and it'll pop up for all of us to see. So the first question is, Yesterday was the 32nd birthday of the Hubble Space Telescope. What was its namesake, Edwin Hubble, most known for? So when you answer, it will pop up here. Telescope. He's most known for a telescope, known for redshift, other things. It's kind of an open-ended question. I mean, this is open to interpretation at some level. He's made several contributions to the field of astronomy. That's why he got a telescope named after him. But I think there's kind of one thing that stands out a little bit more. So we've got expansion rate.
Smoking a pipe, that's worth partial credit.
Wait, what'd you say?
Smoking a pipe
Smoking
is
a
worth
pipe.
partial credit.
Every photograph you see of him, he's like sitting there with this nice, tweed jacket on, just smoking a beautiful pipe. It's
including with his eye looking in a telescope eyepiece, smoking a pipe.
Yeah. So you've got universes expanding, expansion of universe, galaxies, discovering Neptune. I wasn't aware of that contribution. Galaxies, Mr. Hubble, redshift, a telescope, star types, maps, Hubbling. Hubble is known for Hubbling.
Hubbling is a good one.
Yeah.
In, I believe it was 1904, Hubble was a Gold Gloves boxer in Chicago and KO'd the German national champ.
Oh, really? I didn't know that. That's great.
He's not particularly known for that.
Known for that. But I do like this one. He's particularly known for his wonderful cupcake recipes. So indeed, as many people suggested, kind of his primary, the thing that I think of him most known for is the expansion of discovering the expansion of the universe. So he did this on a telescope called the Mount Wilson Telescope, which is just a few miles outside of Pasadena in the San Gabriel Mountains that look down on Pasadena. He did this about 100 years ago. And as this kind of illustration, this cartoon suggests, what he recognized was he would observe different galaxies and he would observe the speed at which they were traveling, the redshift of the light coming from them, which gives you the speed at which they're traveling away from us. And he figured out, this is a nice little plot that shows the ones that are on the x-axis here, you have distance of a galaxy. And on the y-axis, you have the speed with which it's traveling away from us. And each of the dots represents a different galaxy. And as you can see, the ones over here, the ones that are farther away from us, are traveling faster away from us. And the ones that are closer to us are traveling less fast away from us. And you might think that that's pretty weird, right? Like, well, why are we in the center of the universe and the stuff that's farther away from us is traveling faster away from us? And his interpretation of this wasn't that at all. It was simply that the fabric of the universe itself is expanding. And so the stuff that's farther away from us has more space in between us. And because that's expanding, it means that the stuff that's the galaxies that are farther away are actually traveling farther away, not because of any cosmic coincidence that we're in the center and we have really bad breath and everything's trying to get away from us as much as possible. More, it was the interpretation that the universe itself is expanding. The other kind of primary thing for which he's known is simply the discovery that other galaxies exist in the first place. This is a famous image that was taken by Hubble with the Mount Wilson telescope of the Andromeda Galaxy. Everyone is probably at some level familiar with the Andromeda Galaxy. It's our nearest kind of massive galactic neighbor. You can see it with the naked eye in dark skies if you know where to look. Not at this resolution, but you can see it with your naked eye. And this is an image that shows up here in the corner, you can see this dash that's surrounding this single star, and then it says VAR. And VAR stands for variable, and because that star varied in its brightness, and due to a discovery that was made by another scientist, Henrietta Leavitt, about a few years prior, that you could determine the distance to a star based of a variable star based on the frequency with which it brightened and faded in its intensity. And from that, he could basically figure out that this whole structure was really, really far away from us instead of being like within our own Milky Way. At which prior to that, we had basically thought that the Milky Way was the entire universe. And so this really, really, opened the can of worms that there are tons of other galaxies like our own Milky Way throughout the universe. And now we know there's something like, on the order of 200 billion of these structures, galaxies, but we didn't really know that until, at least conclusively, until Edwin Hubble did his business. So do you guys have anything else to add on this?
Well, if you find the color version of this, you will actually see that the cross out of the N and the VAR exclamation point are actually written in red pen to give you an idea of how excited Hubble was, because that N is nova, because that's what he assumed those bright flares were, that the first one was a nova and the second one was a nova and the third one was a nova, and then the fourth one, holy crap, occurred right where the first one did. And Hubble knew that novae take a long time to recharge. Like, I think the fastest recharge we've ever seen is still close to a decade, and more commonly, we think hundreds or thousands of years. But this one went dim and brightened again after like a day and a half.
Yeah.
And like you said, that means no, it's not a nova, it's a variable star. So that cross out and that VAR exclamation point is like, it's justified. It's super exciting, but also Hubble was a notorious defacer of his photographic plates. If you take a look at Walter Baade, who's one of the more famous people who came after Hubble at Mount Wilson Observatory, Baade's slides are pristine. He did not write on any of his slides. So this is like Hubble not only leaving his mark, but like putting his excitement down on it as well. And I guess if you're the first person to discover, oh, the Milky Way isn't the only galaxy in the universe, and by the way, the universe is expanding when I combine these with Vesto Sliefer's measurements, maybe it does deserve the red pen and the exclamation point.
Exactly. Okay, and just as a side note, as I said, yesterday was Hubble's birthday. It's 32 years old. It was only originally the predicted lifetime of it when it was launched in 1990. It was only meant to be 15 years that it was up there, and it has, there have been a few missions that have gone up and replaced some parts and added additional instruments and allowed it to continue to live, but it's still going pretty strong despite a couple of hiccups in the last couple of years. And hopefully, Edwin Hubble himself lived to the age of 63. So, hopefully his telescope will live just as long, despite the fact that now the James Webb Space Telescope has launched into space and is replacing some aspects of Hubble. But yeah, hopefully they'll be able to coexist for a few years at least.
Hubble hasn't been serviced since 2009. So it's been up there in its current form for 13 years. And it's not only still going strong, it's still the best ultraviolet optical observatory we have in the world, or out of this world, I guess.
Out of this world, indeed.
So James Webb and Hubble are actually complements to each other. Their overlap in wavelength range is actually very small. So the idea that we can observe the same object with both Hubble and James Webb is very exciting.
It is. And just another quick point to make. If you go onto Twitter, there's a Twitter account called Space Tele Live that will tell you periodically throughout the day, 24 hours a day, what Hubble is looking at, and give you an image of that particular thing and tell you who is responsible. Because of course it's owned by the federal government, it's owned by NASA, but we as astronomers apply for time to look at this target or that target in the sky, and Hubble is oversubscribed by a factor of 10, so it's really hard to get Hubble to look at the thing that you want to, but if you do a good enough job justifying why it's important scientifically and what kind of science you can do by Hubble looking at this object or that object, then you might get the opportunity for it to point towards your object. So as of a few hours ago, Hubble was looking at a cluster of galaxies, this particular cluster of galaxies, using the instrument, the Wide Field Camera 3, for Dr. Patrick Kelly. And so you can click on that and find out more about that particular science proposal that was justified in looking at that. So it's kind of cool to see like your tax dollars at work looking at astronomical targets and so on and so forth. Okay, next question. Astronomers divide stars into 3 different groups: population 1, population 2, and population 3. What population is our sun? Oh, wow. It's everybody's, okay, here we go. Nice, mixing it up. It's not just a runaway. Ooh, Generation X gets a vote. Nice.
I'm Gen X. I feel like a vote for Gen X is a vote for me.
That's right. It is.
I'm not even running.
It is. So the overwhelming set of responses is for population 1. And indeed, the answer is, in fact, population 1. Would you like to discuss this at all, Ethan? You talked about this a bit during your presentation.
You know, it's kind of funny because the way we named stars by population is we said, what are they like? And we found that like when we started looking at other stars, like kind of a little big handful of them, like maybe about half, were like our sun. So we said our sun, if you're like our sun, it's population 1. And then if you like the other stuff, well, the other stuff, that's population 2. And then we started to say, wait a minute. So all of this stuff, all of these stars, they either look like our sun or they look like they're poorer in metals, poorer in heavy elements than our sun. But in the Big Bang, you shouldn't have been able to make any of these heavy elements. So there's got to be this third population out there. There's got to be population 3. So it goes in reverse order evolutionary. Population 3 stars are pristine. Population 2 stars can only form after population 3 stars have lived and died. And then population 1 stars like our sun, which are the kind we think you need to have like enough heavy elements to have like life on a planet, maybe, which is kind of something we like. Like, no, you need many, many generations of stars and lots of like messy crap. And only then can you have population 1 stars made out of this recycled material of generations of dead stars. So thankfully, everything in the universe isn't a cannibal, but it's kind of this weird naming scheme where 3 is the first and 2 is after that and 1 is like today. Because when we look back, we discover things in reverse order because the things like us are closest to us.
Yeah, I just included that. Oops, I gave the wrong answer here. I didn't update things, but this image shows kind of a perspective image of what our Milky Way would look like if you were looking down on it face on. And the idea is simply that in the core, the bulge area, you see some yellower, what astronomers would call redder stars relative to the blue stars of the disk and the spiral arms. And that's primarily, well, maybe not primarily, but partially consisting of the population 2, these kind of older stars that Ethan was describing, whereas the bluer stars in the arms are more population 1, like our sun. But
you want to find a good population 2 star, look in a globular cluster because they haven't formed stars in many billions of years, or look in the galactic halo. Population 1 stars like to live in the disk. Population 2 stars like to live in the outskirts.
Like this is kind of showing, indeed. And similarly, I guess in the future we'll have population 0 stars that are like super enriched by their metals and so on and so forth. But I don't know. That's probably the distant future.
Oh, fancy! I've never heard of Pop Zero before.
Well, I don't know. I just made it up.
I like it. I like it.
Okay. So related to the content of Sam's presentation, how strong is the magnetic field of the gas in the Milky Way compared to the Earth's own magnetic field? You know, this whole presentation was all about magnetic field strengths, but how does it compare to something that we have a little bit of intuition for, the Earth? Is it weaker? Is it stronger? Is it the same? There is no spoon. There is no magnetic field, perhaps. Oh, the spoons are running away here. Okay, all right. All right. So the answer, it seems like our audience was paying attention. Good, good. It is indeed about 100,000 times weaker. Sam, do you want to talk at all about this?
Yeah, the magnetic field strength of the surface of the Earth that we feel from Earth is about half a Gauss. Those are just units that physicists measure magnetic fields in. In the galaxy, it's something like 5 microgauss, or 100,000 times weaker in interstellar gas, typically.
I see. So that makes sense then when you were talking about how would things in the solar system be affected by the galactic magnetic field. You know, the Earth, if the Earth is, you know, on the order of 100,000 times stronger in terms of the magnetic field, it makes sense that it wouldn't be dramatically impacted by this low level background. Yeah, I just included this kind of stereotypical image of the magnetic field associated with the Earth and how it's influenced by the sun. How much stronger is the solar magnetic field than the Earth's?
It's actually at the sun's surface, it's about a factor of 2 compared to Earth at Earth's surface.
I see. Okay.
Yeah, and yeah, part of the thing too is the distance, right? So in terms of if you have a fridge magnet and you put a fridge magnet on a fridge, the magnetic field strength of the fridge magnet when it's attached to the fridge is like 200 Gauss. It's like,
whoa,
like 200 times larger than the Earth's magnetic field that you feel. But as you get farther away from the fridge magnet, obviously, if you had something that was sensitive to magnetic field, it's not going to be sensitive to the fridge magnets anymore. It's going to be sensitive to the Earth's magnetic field. So part of the reasoning for what field would be important is also how far away you are from the source of the field.
From the source, I see.
It's kind of cool that if you go anywhere in the solar system away from Earth, the sun's magnetic field dominates. Like if you move about like 100 Earth radii closer to the sun's magnetic field dominates. And if you move above the North Pole or below the South Pole, 100 Earth radii, the sun's magnetic field dominates. But if you go away from the sun, the Earth has a magnetotail that dominates for millions of kilometers. And we can actually see the solar wind get deflected as it passes the moon in orbit, when the moon's orbit passes behind the Earth. And that's kind of cool.
That's super cool. Yeah. We'll get back to solar system magnetic fields in a future question. But for now, what company hosted the first fully privately funded space mission to the International Space Station, which landed today? Well, a big SpaceX, but is that the answer?
Wait, do you mean the ISS landed today?
Oh, no, I guess that was poorly written. I mean, the first privately funded space mission to the ISS landed today. The ISS is still up there, still kicking strong, thankfully. Twitter, Amazon, SpaceX, it's axiomatic. Outback Steakhouse. That always makes me chuckle. The Outback Steakhouse. So it's kind of a trick question. Not really. SpaceX is kind of partially correct. the correct answer, the fully correct answer is this company called Axiom Space. So Axiom Space is a private company that hosts launches using SpaceX rockets to go up and do privately funded missions to, right now, to the ISS. Today was their first mission to the ISS. This is one of their astronauts. So there were four people who went up to the International Space Station, and they spent 2 weeks up there, and they just came back today. And I believe the people paying, because it was private, they each paid over $50 million for this 2-week little vacation, which, you know, if you've got the money, that sounds pretty sweet, to be honest. But they went up and did a bunch of work and science experiments, and were doing things aboard the ISS in the microgravity environment that you experience there. And I guess this is meant to be the first of many missions to the ISS that Axiom Space is going to do. And what's more, in the process of doing so, they're going to be bringing up like chunks of a new space station that eventually they'll put together, kind of appended off the end of the ISS, and then will disconnect from the ISS and be its own private space station that's also in near Earth orbit, and that will be a location that you can, you know, if you have sufficient money or you are one of their clients, that you can visit. So that's, I mean, at some level, that's pretty exciting. The ISS has been around for quite some time and is kind of set to expire in the next few years. So having something up that's new will be cool. And I know a number of other private companies that are looking to do something similar. I think Blue Origin, the Amazon version of this, is also trying to make some sort of private station. I think multinational governments are also trying to do this, but this is kind of the first step. And yeah, sure, there's going to be a lot of crowding in low Earth orbit, but hopefully not so much that it causes problems with other people going up as well. So I don't know. It's interesting. It's kind of exciting. It kind of caught me off guard that we were at the level of doing this sort of thing yet, but here it is. Do you guys want to go to space? If you had the opportunity to go to space, would you go, Sam, Ethan?
Do you want this to stay PG?
Oh my. At least PG-13, perhaps. Yes.
Look, experiencing space, being in the zero gravity environment of space is like a childhood dream of not only mine, but of many, many people. But when I look at the scientific value of going to space, I don't think I should be the person to go. And when I look at what the cost is to the environment and to all the other people on Earth, and when I think of the good that $50 million could do, boy, I would have to be a very different person to think spending it on myself and my experience to go to space was a good use of that funds. But also, I think the idea that we would decommission the International Space Station, which is a symbol of international cooperation in the space age, to replace it with whatever Jeff Bezos or Mark Zuckerberg, or he's not even doing it, but
no, I don't think he's doing it. But I get your point. Like one of the tech billionaires or something.
Come on, like, is this the best we can do as a species? Is this really the decisions we're making and we think are worth it? I know plenty of you will think, yes, you commie bastard, but PG-13 as I'm getting.
I appreciate your candor. I agree with you largely. I don't think that the ISS will be decommissioned at, right now. I think it's set to be decommissioned in 2024, but there's a proposal to extend it to 2030 at least.
I mean, you got to remember former NASA administrator Sean O'Keefe wanted to decommission and deorbit the Hubble Space Telescope in the early 2000s. around 2003, 2004. And the winner of the, I don't remember if it was Westinghouse or Intel Science Talent Search, when he got up on stage to shake then President George W. Bush's hand, he said, "Mr. Bush, please save Hubble." And Bush, in his infinite Bushism, said, "Is Hubble in trouble?" And long story short, we did not deorbit Hubble, but the idea that we would deorbit the International Space Station, I think, look, I still look forward to the possibility of a world where we cooperate as a species to advance the collective good of humanity. And that might make me hopelessly and endlessly naive, but that is the kind of future that I myself find myself working towards. And so if we can move towards a future in space where everyone benefits collectively on the planet, that's really a much bigger priority for me than any, personal satisfaction I might get from a few minute or hour or week journey into space.
Agreed.
I agree largely too. If it was for something that wasn't just like going to space for fun, yeah, that's something that was actually good use of resources and time. Mhm.
Doing some sort of magnetic field study of the near Earth orbit, perhaps.
Maybe.
No, I agree. I think that's well said, and we should focus on optimizing the use of money to benefit the species, and not just vanity plays like some of these efforts have been. I agree. Okay, so getting back to magnetic fields, what planet in the solar system has the strongest magnetic field? Strongest magnetic field. Let's see what people think. Remember, no reason to look it up. You could just guess. You could say Earth. Earth is the strongest, biceps.
It's the fridge magnet.
Earth is the only planet with biceps, as far as we know.
Ah, yes, when Pluto was a planet, it reigned supreme because of its dominant magnetic field in the Kuiper Belt.
Pluto fans might love to know that although Pluto is currently the largest orbit object in the Kuiper Belt, back in the day, Triton, Neptune's largest moon, we know that Triton originated from the Kuiper Belt. Right. And Triton is both a larger, more massive, has more cryovolcanoes, and I believe, but I'm not sure we know for sure, but I believe Triton has a stronger magnetic field than Pluto does.
I don't know. It may very well.
I don't know that either. I don't know that for sure. I believe it, but I'm not sure. Okay. That might be, if you wanna look something up, go look that up.
Yeah, that's fair. Some good answers. Oh, Planet 9. Yeah, perhaps that's a possibility. The answer is indeed Jupiter. Yeah, its magnetic field is several thousand times stronger than the Earth's magnetic field. But you can see here, there's this kind of composite image. You can see the bluish color of the aurora, the aurora borealis, the northern lights. Jupiter also has this, and it was observed decades ago by the Hubble Space Telescope and other telescopes. You can see it in the UV, you can see it in the X-ray, you can see it in the radio, due to the powerful emanations of electrons and ions interacting with the Jovian atmosphere. But what's cool about this is, unlike, when you always get these alerts in the news, because the news loves to pick this up, because the aurora is super cool, right? Have you two had the opportunity to see the northern lights or the southern lights before?
I've seen the northern, but not the southern.
Yeah, I saw the northern lights once on a plane.
Oh, really? Oh, wow.
Mm.
Like it was a intercontinental flight where you flew over the North Pole, or you went through
It was,
northern Canada or something like that?
yeah, it was transatlantic. So it must have done one of those like large loops up north. Yeah.
Cool. I'll bet that was awesome. Did you see the curtains and stuff, or was it just kind of a
Really brief.
glow?
Yeah, just kind of the glow. Yeah.
What did you see, Ethan?
I got to see the curtains once when I was in Glacier National Park in Montana.
Whoa.
That my friend who I was camping with just kind of knocks on my tent in the middle of the night, and he was like, "Hey, Ethan." I was like, "Yeah," and he was like, "What do the Northern Lights look like?" And I was like, okay, I'm coming out. And so I came out, and yeah, there was that green curtain shimmering back and forth. I was surprised at how fast it moved. I was expecting it to be like one of those time lapse things where it would be like, okay, now it moves. Like, no, it was like real time, like I'm making my own sound effects. There were no sound effects.
Well, so the Earth-based aurora is primarily, and most of the planets, is primarily due to activity in the solar magnetic field, much like we were talking about before, and solar wind particles coming out and interacting with the Earth's magnetic field. But with Jupiter, it's largely internally driven as opposed to by the solar magnetic field. This is an artist's rendition of kind of the magnetic field of Jupiter kind of interacting. You've got this little bow shock sort of thing due to the solar, but most of the magnetic field the aurora associated with Jupiter is due to the interaction between Jupiter's magnetic field, and its most massive moons. So this is kind of a zoom in on one of these Hubble Space Telescope images of the polar region of Jupiter and the aurora, the northern lights from it. And what's super interesting about this is you can see these dots. And these dots are specifically from the Galilean moons, from the most massive moons that orbit around Jupiter. They basically act as flux tubes for electrons. So this is an animation kind of showing that. And again, you can see these dots. And essentially what happens is you've got Jupiter orbiting, and its magnetic field extends way, 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 way out because it's super powerful. And the moons that are orbiting at a different rate than the magnetic field is rotating with the rotation of the planet. And that excites essentially electrons and ions that come off of those moons and then flow along field lines directly into the polar regions of Jupiter, and they act as flux tubes. So essentially it's like a drinking straw where electrons are traveling through that drinking straw along that magnetic field and dropping directly onto the polar regions of Jupiter. And when that drinking straw full of electrons hits the atmosphere, it excites the region around that with photons, with light. And that's what we're seeing these little dots are. There's also this other behavior, which you can see is quite erratic, which is generated by a different phenomenon, which is partially understood, although I was reading a couple of papers on this, and it doesn't seem like it's fully understood, this behavior. But certainly the moons and their flux tube behavior is reasonably well understood. But I think that's super cool. It'd be awesome if we had like a point of light in the upper regions of Canada or the northern United States that was caused by our moon, but sadly we don't have strong enough magnetic field, and there's not enough of an interaction between our magnetosphere and the moon to generate such a thing. But I don't know. I just thought that was super, super awesome. Okay, I think this is our final question for the night. What NASA mission is undergoing tests today after some issues it has encountered over the last month? I guess that's a vague enough question, but I imagine some people may get this nonetheless. There aren't that many NASA missions that, I guess actually that question could probably apply to like 10 different missions, but there's one in particular that I was looking for. So James Webb, Artemis, Artemis 1, Artemis I.
You get bonus points if you read Cameron's mind.
That's right. Bonus points. Exactly.
Yeah. Things Cameron doesn't care about. NEO surveyor. things Cameron doesn't care about, the nicer mission.
Oh, I
Things
care
Cameron-
about NEO Surveyor. I care a lot. I actually just applied for a job with NEO Surveyor, but I was turned down. So sadly. For those who want to know, NEO Surveyor, we had Amy Meinzer, who was on the program in December, who is the PI of NEO Surveyor, which is a super awesome mission to look at all the near Earth objects greater than the size of roughly a kilometer that have the potential for running into the Earth at some point in the future. So essentially trying to track all these asteroids and structures that might have an encounter with the Earth so that we can better understand what our chances are and better prepare for that and divert them if the technology becomes online for us to be able to do that. Beer, always a good, Cameron's mind.
I like Hubble's Space Telescope. Yeah. You've got a fan there.
I like that one. I like that one. So indeed, the answer for those of you who were able to read my mind is Artemis 1. So Artemis 1 had gone in kind of a test run. They had moved the ship to the launch pad from the building where it was essentially assembled about a month ago, and encountered all kinds of issues along the way. So they brought it back to work on it. And tonight, let's see if this works. There is a live feed, which was meant to start 40 minutes ago, of that mission being brought back. So this is a live YouTube feed, and I don't see a lot of.
See it, do you?
I don't see a lot of movement. Maybe it was delayed again. But for those of you who aren't aware, Artemis 1 is the first in the series of the Artemis missions. Artemis being the goddess of the moon and being kind of the successor to the Apollo missions, which first brought the astronauts to the surface of the moon in the 60s and the early 70s. So the first of these missions is meant to occur, well, at some point this year, although depending on how the results of this new test go, may affect that timeline. But I think they expect, if everything goes as planned, then it'll happen sometime in July or August. And this is an uncrewed mission that will go up and I think it's spending a few weeks orbiting around the moon and just testing out systems to be able to lead to Artemis 2, which will have a crew and will be going up and orbiting around the moon, much like some of the Gemini and early Apollo missions did. And then finally, Artemis 3 is meant to have a crew that lands on the surface of the moon, but that won't be for the next few years. So yeah, this movie is not unfortunately showing anything, but you get the idea nonetheless that it will be essentially, they walk this thing out, this enormous SLS rocket that looks a bit like this. This goes on a little slow-moving tank that travels 4 miles over the course of like 12 hours, so that it doesn't, introduce any kind of rocking or momentum that might damage the structure. And then it gets to the launch pad, and then they test it all out, and then make sure it's good to go, and then do the real deal in a month or two. So anyway, I think those are our questions, and those are our answers. So thank you all audience members for your quiz. I hope, it seems like most people got the right answers, and when they didn't, they at least came up with some clever responses. So I guess that brings us to the end of the night overall. I want to thank Dr. Ethan Siegel and Sam Panada for your excellent presentations and communication to our audience. It was a pleasure having both of you on. I certainly learned something from both of you, so I appreciate that.
Thanks for having us.
Yeah, it was a fun experience. And if any one of us knew it all, science would be a very, very boring place. So it's only because there's so much to know, and there's so much to learn, and there's so much that we're still discovering with each little increment of time that goes by, that this is the exciting endeavor that has captivated so many of us.
Well said. Well said. That's why you're a highly prized science communicator. And what's primarily right now your material is on Big Think? Is that correct?
It is. If you want to know anything about me that you didn't cover here, my doing business as name is Starts With a Bang. So if you're like, where's Ethan and what's he up to? Just go to startswithabang.com or Google Starts With a Bang, or look for Starts With a Bang on Twitter or Facebook or SoundCloud or wherever you like to look. And either it's me or some cheap imitation.
Excellent. And where can people find you, Sam?
Oh, I'm probably making a website soon,
Okay.
but yeah, I have a Twitter, but
Okay.
I haven't really used it for science much yet.
That's fair. I don't use mine much for science either.
But yeah, I'll probably make a website eventually. But if you Google me, or
yeah, and I hear you're going to have a paper out on this pretty soon, so
yeah,
excited to see that.
Yeah.
So I'll keep an eye out in the Astrophysical Journal or monthly notices of the Royal Astronomical Society, wherever you submit it. But yeah, thank you both for your presentations tonight. Audience members, thank you for sticking around and taking your Monday to join us and to learn a little bit more about science. And yeah, as I mentioned at the beginning, our next event will be in about 2.5 weeks. We'll have a stargazing lecture given by young Professor Katerina Hatziuanu, probably about gravitational waves and pulsar timing arrays, although I haven't yet gotten a title from her. And then our next Astronomy on Tap, that will be May 13th, Friday, May 13th. And our next Astronomy on Tap will be Monday, May 23rd. It'll be given by Dr. Mike Wong and myself. His talk will be the science of Star Trek, and mine will be the science of Star Wars. And we'll talk about those science fiction universes and the science associated with them, and kind of contrast and compare. So stay tuned, and we'll be back soon. So thanks, everybody. Have a wonderful, Star Trek technology. You have a book that you wrote on Star Trek.
So I have a horse in the Star Trek versus Star Wars race. And I wasn't going to say anything, but if that's what you're going to be talking about next week or next month,
I'll have to get you back on.
I can highly recommend this book. I can highly recommend it. If you are interested at all in the technologies presented in Star Trek and how close we are today to achieving them in real life, this book comes highly recommended to me. And if you don't trust my recommendations of the book where the author has the same name as me, I can recommend, look up the reviews on Amazon. They're pretty accurate.
Awesome. Well, I will read up, and I will definitely cite that book in a month, and maybe we'll have you back on as well.
Well, twist my arm a little bit. It'll happen.
Cool. All right. Well, thanks everybody for joining.